Hi everyone! Alright, so in this video we're going to do a quick introduction to the Taylor and Maclaurin series. And so, let's start off with the Taylor series. So the Taylor series is a way to expand a function. So let me write that down. It's Taylor series expansion. Okay. So, what is it? So let's say if f of x is represented by a power series that's centered at C. I'm gonna make C a different color. Let's C. Oops. In an interval. Okay. X minus C is less than R with R greater than 0. So you have some limitations. Then the power series is the Taylor series. And that is T of X equals the sum of n equals 0 to infinity of f of n c over n factorial times x minus c to the nth power. Okay, and so this is your key formula for the Taylor series. Okay, good enough. Okay, and so on the flip side, the Maclaurin series, how do you spell that? L-A-U-R-I-N. Okay, series is the Taylor series, except it's centered around 0. So C equals 0. So basically, same as Taylor series, except C equals 0. Okay, and so that looks like f of x equals the sum equals 0 of f of n centered at 0 all over n factorial of x to the n, which is just basically plugging in 0 where c is in the Taylor series equation. And so let's do a quick example of this. Let's see now. Okay. Example. Let's find the Taylor series for, let me write this part in a different color, f of x equals x minus, oh, I should have wrote that lower. Went too much. Where's the undo button? Okay. Taylor. Okay. F of x equals x to the minus 3 at, oh, that was ugly, at c equals 1. So I wrote in gold what we need for the Taylor series equation. So let me rewrite the Taylor series equation so it'll be easier for us to work it through. Okay, let me scroll up to here. Okay, So the Taylor series equation is Tx equals the summation of n equals 0 of f of n centered at c all over n factorial times x minus c to the n. Okay. So let's break it down. Let's find, this is a highlighter. Okay. Let's find this part first. Okay. It's a weird highlighter. Let's start with this. So let's do the first couple derivatives. So let me see. The first derivative of f of x equals minus 3x to the minus 4. And f double prime equals minus 3 minus 4 x to the minus 5. And so from here, you kind of have to see if there's a pattern. And so you have to look closely, see if there's a pattern as n increases, or as the order of derivative increases. And so, as you can see, the negative 3 and the negative 4 stays. So you start with negative 3 as your coefficient in your first derivative, and then you add the negative 4, and then you add a negative 5 as it goes on, negative 6. And so you know that as n increases, you're going to have that like continuation. And so one way to do it, you could write it as n plus 2, because for the first derivative, it was a 3, so that's plus 2, and that's factorial. So this gives me, say, so that would give me like at 1, n equals 1 would be 3, and then at n equals 2 would be 3, 4, and it'll continue. All right, so we got that part. But the problem is with the factorial, you have there's a 2 in front of it, because it'll go from 1 times 2 times blah, 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 to n plus 2. So how do we get rid of that 2? Divide by 2. Okay. All right. And then, that's good. We also have to deal with this negative. So in the first derivative, it's a negative 3. In the second derivative, the negative 4 multiplies with negative 3 to make a positive number. And so that means, oh God, the negative sign switches. So it'll be positive for n that's even and negative for n that's odd. So one way to write that is just minus 1 to the nth power. Makes sense? Because when n is 1, it'll be negative 1. When n is 2, it'll be negative 1 times negative 1, which is positive. And so that is the first part. And so to make it easier for us, we could already plug in 1, which would be, oh, I missed this piece. I was like, I'm missing a piece. Okay, and then now we have left is the x. So you know there'll be an x. Oh, God. And so first derivative is x to the negative 4. Second one is x to the negative 5. And so it'll be your original function, negative 3 minus n. Because that's just the simple definition of a derivative, the power rule. And so from there, since this is centered at 1, we can plug in 1 into our x's to simplify it. So that's n plus 2 factorial all over 2 to the x. Oh, wait, that's just 1. That's just 1. Okay. So we have the first part. Bam. First part. Next part. Let's include this factorial. Okay. So that factorial is f. Ooh, wait, I'm still highlighting. F to the n of c all over n factorial. That's just take what we got from before all over 2. Right? That's my fn. Here, let me plug in 1. It's 1. Okay. And then we're multiplying it by 1 over n factorial, which equals, what does this equal? Well, if you look closely, you have n plus 2 factorial on top and n factorial on the bottom. And so let's say n is 3. So the top would be 1 times 2 times 3 times 4 times 5 because it's plus 2. And the bottom will be 1 times 2 times 3. And so this would always cancel, leaving 4 and 5. And so this simplifies to n times n plus 1 times n plus 2 all over 2. Sorry, I had that sneeze. So this becomes that. Okay. So we got the coefficient of our Taylor series, which is what I highlighted in pink. And the rest is simple, actually. So in the end, it'll just be t of x sum of n equals 0 to infinity of that coefficient we found, which is this one. So that's minus 1 n times n plus 1 n plus 2 all over 2 times, what's the rest of it? X minus c, which is just 1 to the n. And that is your Taylor series approximation. So this is your final answer. Okay. There you go. So when you're solving the Taylor series expansion, it'll be easier for you to expand it to the first couple of terms and then try to see if there's a pattern, because most likely there is. And yeah, that's it for this video. Thanks for watching.